So 2 announcements, which are that homework number 4 is due this Friday at the beginning of class, and then homework number 5 is due next Friday. So be sure to have those ready and on time. So last we left off on Friday, we were talking about PCA, and we had motivated PCA as trying to find a projection, a subspace given by this blue line here, which both minimizes the projection residuals, so minimizes the error between the red line and their projection, the red dot and the projection onto the blue line, and also maximizes the variability in the data that captures the structure in the data. So let's say that this dot that I'm circling here in green corresponded to a reach to the right, and this dot that I'm coloring in purple corresponded to a reach to the left. Their projected values are still very different along this blue projected axis. And so that's capturing the variability in these data points. Oppositely, we could have a bad projection that looks like this blue line here. And what it does is it has a lot of errors between these data points and their projections. And also, we've lost the meaningful structure in the data. So here, if we circle our rightward reach and our leftward reach, and we were to project them onto this axis, because this axis is so poorly aligned with the data, the purple reach might project here, and the green rightward reach might project here. And even though these 2 data points were very different in the natural space, in the projected space, they almost look identical. And that's not what we want. And so we were saying that PCA was the way to do this, to find these good projections. And so I'm just going to actually unpack a bit more the terms here, since there are a few questions about those. So we'll define this axis here as, for now, principal component 1, the best axis that we can have. And this axis is always a unit vector. So PC1, for example, because it points at 45 degrees, would be equal to 1 over square root of 2, 1 over square root of 2, where the square root of 2 is just a normalizing term so that the norm of PC1 is 1. Okay? And then what we said is that the length, the distance from here to here, was equal to PC1 transpose xi. So xi here is a vector corresponding to this red data point. Okay, so this xi would be equal to something like 1.0, 1.5. So it's the data in 2D space. And what we said was that PC1 transpose xi was this distance here. And why is that? Well, we know from our dot products that if we have 2 vectors, A and B, and we take their dot product, this is equal to A times B, their norms, times the cosine of the angle between them. All right? And so if I call the red vector this one A, and I call this vector, we'll make it orange here, B, then because this is a right angle and this is theta, then we know just from our geometry that this length here is equal to the length of this times cosine theta, right? And so now let's just plug in values. So here we'll say, so if A were xi and B were PC1, then B would go away. It has a norm of 1. And so this dot product, A transpose B, is just equal to the norm of A times cosine theta, the length of A times cosine theta. And from our geometry, that's exactly the length of this point. All right? And so this is the first dot product that you took in your vector calculus class. All right, so PC1 transpose xi is a number, a scalar. Let's call it 0.7. That represents the magnitude from here to here. And so if we wanted the vector of where this orange point was in 2D space, what we would have to do is we would have to multiply the length of this vector by its orientation. So this vector is oriented along PC1, and its length is PC1 transpose xi. So this orange point here would just be PC1 transpose xi times PC1. All right? Is that clear to everyone? Are there any questions on this? All right. So then if we go ahead and we want to calculate what this residual is, well, now in this equation, we've just made it general. Instead of calling it PC1, we've called it U. And so in this picture, PC1 is equal to U. Then this orange point here, right here, would be U transpose times xi, its distance, multiplied by the direction that it's going, so multiplied by U. And so then if I wanted to calculate what this dotted blue line, which I'll draw here in green, is, then all I'd want to do is I'd want to take the vector sum of, or the vector difference of this red vector minus this orange vector. All right? So in this equation that we have up here, the red vector is just this term xi. This minus U transpose xi U corresponds to the orange vector. And so if I subtract them, then what I get is this green vector here. And then when I take the norms squared, then all I'm doing is summing the distances, the lengths squared of these green vectors. And so that's why for PCA, when we say we want to minimize the residuals, this is the cost function that we can write. Any questions on this? All right. So we're now going to go into how we actually solve this optimization equation. And we're going to derive how we arrive at the PCs, but there's some things in this derivation like Lagrange multipliers and a vector derivative. And you will not be responsible for knowing the details of that. We just wanted to put it here for completion so that you understand that this isn't completely magic. All right? All right, so we're going to take our cost function. Remember, it had this 1 over n term as well. This is the thing that we wanted to minimize with respect to u. And we're just going to drop the 1 over n for now because the 1 over n is just a scaling term that we can ignore. And so the first line here, we're going to take advantage of the fact that we know that the norm of a vector squared is the same thing as a dot product with itself, right? Because this y transpose y is equal to the first element of y times the first element of y plus the second element of y times the second element of y, etc. And this is the sum of its squares. And so this will give you y transpose y will give you the norm squared of y. And so I'm going to take this big term in here, which is squared, and just write it as itself transpose itself, the dot product of the term with respect to itself. And now what we have to do is we have to just go ahead and we have to just expand all this algebra. And so we're going to now make use of an identity from linear algebra that if you have 3 matrices or vectors, A, B, C, and you take the transpose of all of them, that's equal to C transpose times B transpose times A transpose. And so this is something that you could work out. Again, you won't be required to know this for the final. So the transpose does distribute, but then what it does is it just permutes the order of your terms A, B, and C. And so what I'll do is I'll take here xi transpose xi. And so this is the first term times the first term. That gives me this right here. I'll take this term. So I'll have this transpose hitting these 3 vectors. And that'll give me, Then I'll take this term times this term. So I'll have xi transpose here times u transpose xi u. That's right here. All right? And then I'm going to take this term, apply the transpose here. So this whole term will be just flipped over with all the transposes changed. So this u becomes U transpose. This xi becomes xi transpose, and this U transpose transpose just becomes U. And this multiplies xi. And then the same thing for the last term. All right? So all I've done here is I've done our FOIL, or just distributing out all of these terms to arrive at this expression with 4 terms here. Alan?
So dot 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 is not really anything.
Oh yeah, the dot 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 is just meaning I couldn't fit it all on this line here, so it just carries over to the next line. Thanks for clarifying that. Any other questions on the second equation? All right, so then at this step, what I can do is these first and these this first term will remain the same. But you'll see for the second term here, we had xi transpose U transpose xi times U. And what I've done is I've basically I've rewritten this as U transpose xi times xi transpose U. So I basically brought this term to the front of the equation, and I put xi transpose over here. All right? Can anyone tell me why I'm allowed to do that? Alan?
It's a scalar.
Exactly. So, so this term U transpose xi is just a scalar, as Alan said. It's a dot product. It comes out to be a number. And so if I have a vector, right, let's call it 0, 1, times a number, 0.7, I could put that 0.7 either after it or before it. It doesn't matter. It's a scalar. It can commute in any order. And so because this U transpose xi is a dot product representing a scalar, I can just bring it out in front. And so with that, I get U transpose xi transpose U. And then I've done the same thing for these third and these fourth terms, where I've just rearranged them by putting the scalars out in front. All right. Is that clear to everyone? All right. And then in this last step, what I've done is I've taken this U transpose xi times xi transpose U. And what I've said is that this is equal to U transpose xi times U transpose xi. And why can I do that? Anjali? Exactly. Yeah, so it doesn't matter what order you take the dot product in. If you have x1, x2, x3 times y1, y2, y3, right? This is equal to x1, y1 plus x2, y2 plus x3, y3. But I could have easily just written the y's here and the x's here, and you would have the same thing. You would just have y1 times x1 plus y2 times x2, but these are all scalars. All right? The other way to see it is just that, as Alan mentioned, this U transpose, or this xi transpose U is a scalar. And 0.7, a scalar, transpose is just equal to 0.7. Because there's no way to the transpose of a scalar is equal to just the same scalar. All right, so when we change this to U transpose xi and U transpose xi, then we get minus 2 U transpose xi squared. All right. And then this term here will make a U transpose xi, so we'll also get a U transpose xi squared out. And then we'll have a U transpose U term. And what is that equal to? Yeah, 1. Yeah, so remember that in our previous slide, we had that this constraint that our PCs, or our dimensions, they have a norm of 1. And so this U transpose U is just U squared, which is equal to 1 squared, which is equal to 1. All right? So this term U transpose U will cancel away. And so what we're left with then is this term that we've just taken from the previous slide. And now we'll have that this U transpose xi squared is just going to cancel one of these U transpose xi squareds that I have. And then I get this term over here. All right, so after all that algebra, we arrive at something very simple. And what we see is that, remember that we want to make this term as small as possible. And all we got to adjust were these u's subject to the norm of these u's being 1. And so if I want to make this term as small as possible, well, this first term here has no dependence on the u. So it's going to be some constant that I can't control at all. So this is just equal to some c. And then we have a minus u transpose xi squared. So if I want to make an aggregate this whole thing small, it corresponds to making this term here as big as I can make it. And so minimizing these residuals corresponds to maximizing this term here. Does that all make sense? All right, any questions so far on any part of the proof? All right, so we want to make this term as big as we can. So how do we do that? Because this seems like a pretty simple problem. Well, we're going to have a closer look at this term and see if it reminds us of anything. So first, we're going to consider this case where the xi are 0 mean. And it's going to be the only case that we have to consider. And the reason this is because if I have a bunch of data points lying in 2D space, like this, what I can always do is I can always zero center them. I can subtract away their mean so that they look like this. I've just displaced them down so they're centered around 0. And you'll see that if I were to find PC1 on the 0-centered data, which is this purple line here, it's very easy to see what the best line of fit going to the blue data would be. It would just be this purple line displaced upward. We'll now draw it with the green line by the mean. Okay? And so it just simplifies our life to not ever have to worry about fitting this mean as well. It's an extra parameter that you can think of as we've taken it away. We've just set it to 0, and we never have to worry about it. So we can always just zero center our data, find PC1 in this way. And if you did want to work with 0 mean data, you could just offset your axis. All right? And then because xi is 0 mean, our data is 0 mean, it turns out that u transpose xi is also 0 mean. And this is due to the fact that these are linear operators, right? And so if I take a sample, if I want to calculate the sample mean of the x's, this is equal to just averaging all of your data points. 1 over n, I equals 1 to n of xi. Okay? And if this thing is equal to 0, then we have that u transpose xi, the average of this, is equal to 1 over n sum over n of u transpose xi. I equals 1 to n. But then we'll see that the u here doesn't have any dependence on the i's, right? And so we can bring it out of the sum. And so this term here would simplify to u transpose times 1 over n sum of xi. And this is equal to u transpose times the mean of x. And if the mean of x is 0, then this entire term equals 0 as well. And so this is something called the linearity of the expectation or of the mean operator. All right? So if we set our xi is equal to 0, and then we set these then we'll get that these projections, these u transpose xi's, their mean is also equal to 0. And so if that's the case, then this term here, 1 over n, sum of the u transpose xi squared, is actually just the variance of our projected data. And how do we see that? We'll just write out the equation for variance, which is just the expected value of this term here, u transpose xi minus its mean, all of it squared. The mean, we've already said, is 0 because we performed this 0 mean centering operation on the data. And so now we just have that this is equal to the expected value of this term, u transpose xi squared. And we know how to calculate these expected values. We just take the average of the u transpose xi squareds, which is 1 over n, sum of I equal 1 to n of the u transpose xi squareds. And so this term here is actually just equal to the variance of your projected data. Okay. Was there any part of this slide that Didn't make any sense? Does anyone have any questions on it? All right, so when we say that we want to maximize this term, what we're equivalently saying is that we just want to maximize the variability of our data. And this makes a lot of sense given our previous picture where we drew the projected data and we saw that when we had minimum residuals, that also corresponded to having a large spread of variance along our projected axis. So what you can think of as a PCA is finding the projection that minimizes the projection error, the residuals, onto your PC. But you can also think of it as a projection that captures the maximum variability in your data. All right? OK. So these two problems are completely equivalent, as we just stated. And what we can then do is we can pick to optimize whichever question we have an easier time with. And so it turns out that maximizing this will be pretty simple to do with our linear algebra machinery. And so how do we maximize this term, variance of U transpose xi? Well, what I'll do is I'll first rewrite it into a form that will be amenable for later operations. And so what I can do is I can write a matrix X, and this is the boldface X. I'll write it with 2 lines through it. And what this is just the concatenation of all of my data points. OK? And so now if I calculate X transpose U, what I get is I get terms that look like this: x1 transpose U, x2 transpose U, etc. And then if I take the dot product of this matrix with itself, then I'll get a summation of xi transpose U times itself, xi transpose U, from I equals 1 to n. Because all I did is I took this here, x transpose U transpose times x transpose U. It's just the dot product of these 2 vectors. And so that gives me xi transpose U times itself. And that's equal to xi transpose U squared. And we know that because it's a scalar, this is just equal to U transpose xi squared. So all I've done is just rewritten this as in the form of a matrix times a vector. But if I go ahead and I expand this term, right, I'll apply the transpose distribution that we talked about before. So this term will turn into U transpose times x. Then I can rewrite this variance term as this equation right here. And then what I can see is that 1 over n, this term here, times xx transpose, is actually the covariance matrix of x. And so this is the same equation that we used in our Kalman filter, modulo a small term. In the Kalman filter, it was 1 over n minus 1 times xx transpose. And this is just because when you calculate the sample mean, to make an unbiased estimator, you have to change this term n to n minus 1. But anyways, this matrix here, 1 over n xx transpose, is exactly the covariance matrix, the definition of covariance matrix. And so this shouldn't be here. What we can do is we can simplify this entire term to just equal U transpose times the covariance matrix of x times U. All right? Are there any questions on this part? Yeah.
For the second last line to be equivalent to the last line, the 1 over n is needed?
Yes, or because this is just basically taking if you have more data, if you have more samples x of n, you wouldn't want this this xx transpose to just grow uncontrollably. In the end, it actually doesn't matter because all it is a scale term on it. But then formally, the covariance matrix will just normalize these measured correlations or these xx transpose by the number of samples that you use to calculate it.
Thanks.
All right. OK, so all we have to do now is we've calculated that variance of U transpose I is just equal to U transpose sigma x U, where this sigma x here is the covariance matrix of your data. So we just want to pick the directions that maximize this product. OK, any questions on this? All the steps clear to everyone? All right. And so this is the last slide of the proof. And here we're getting into the land of Lagrange multipliers and vector derivatives. And so again, you won't be required to know this. And it's here just for the sake of completion. And for those of you who have had exposure or want to work out this math, these are the answers that you get. And so if we want to minimize or if we want to maximize some term U transpose sigma xu, what do we usually do? So U transpose sigma xu is just a scalar cost function. So how do we maximize things? Yeah, we take the derivative and we set it equal to 0. But now we just have this one constraint, which is that we also wanted our norm, the u's, to be equal to 1. And so when we have a cost function that we want to optimize subject to a constraint, what we use is a Lagrange multiplier. And so all the Lagrange multiplier is your cost function minus lambda times your constraints, written in the form that the constraints are equal to 0. And so what do I mean by this concretely? This u, norm of u equals 1, is equivalent to just squaring both sides. Norm of u squared equals 1. And this is equal to u transpose u equals 1. And this is equivalent to u transpose u minus 1 equals 0. All right? And so here I take my cost function, which is just u transpose sigma xu. And then I subtract lambda times my constraint. And my constraint is just u transpose u minus 1 equals 0. And that gives me my Lagrangian. And then we proceed in the same way. To optimize this, we just take the derivatives and we set them equal to 0. And so now we have two unknowns here. We don't know the u's and we don't know this variable that we've introduced, lambda. So if we first differentiate this entire term with respect to lambda, then this first term goes away because it has no lambda in it. And the second term is just lambda times some scalar, u transpose u minus 1. And so all this gives me is u transpose u minus 1, because this is the scalar multiplying our lambda. Okay? The second term is more complicated because it's a derivative with respect to a vector. And we won't derive this on our own in class because it'll just be time consuming. But the derivative of any scalar, let's say that we have a function a, or a scalar a, and it's a function of the vector u, which means that it's a function of u1, the first element of u, u2, etc. Then the derivative of a with respect to u is just equal to this vector, the derivative of a with respect to u1, derivative of a with respect to u2, etc. All right? And so if you go ahead and you actually just calculate this term for this cost function, you'll arrive at this term right here. And again, you won't be responsible for knowing any of this for the final. We just want to put it in here so that you could get the entire derivation done through. Gary?
Is the differentiation by lambda, was the negative sign dropped?
Yes, I dropped the negative sign. This should be all multiplying -1. All right. Thanks, Gary. And so after we do this, to optimize this, all we want to do is set these equal to 0. Okay? So if we set these two terms equal to 0, what we get is that from the first equation over the lambda, u transpose u equals 1. This is just our constraint. But then from the second equation, oh man, okay. We'll just bring this 2 lambda u to this side and cancel out the 2's. And that will leave us with sigma xu equals lambda u. And so that's this equation that I write here. All right? And so this is a familiar equation if you've had linear algebra before. This is just called the eigen decomposition of the matrix sigma x. Right? And so we knew from linear algebra that if you have a matrix A, it has an eigenvalue decomposition where you can multiply this matrix A by some vector u, and that'll just equal a scaled version of the vector u, where it's scaled by this parameter called the eigenvalue. And so what we can do to optimize this term for PCA is we could just take our covariance matrix sigma x and perform an eigenvalue decomposition on it. All right? And so this vector u here is called the eigenvector. And lambda here is its corresponding eigenvalue. And it turns out that for these covariance matrices, we have this added benefit that all these u's are completely orthogonal to each other. And so, we would, if our sigma x was an n by n matrix, well, we would get, let me use a different term because n was the number of data points. If it was an m by m matrix, so m is the dimensionality of our data, then we would get out a u1, a u2, all the way to a um. This is what the eigenvalue decomposition would return to us. And these u's all have norm 1. And it turns out that the dot product ui transpose times uj would be equal to 0 when I doesn't equal j. And this just means that these dimensions are orthogonal to each other. And this is actually a nice property because what this is doing is it's giving us an orthogonal basis that captures a lot of the variability. And we know that the different dimensions, so u1, for example, would be dimension 1. u2 would be dimension 2. u3 would be dimension 3. We know that these dimensions are uncorrelated. They're independent. Okay? All right, so that's the eigenvalue decomposition. It'll return us these vectors u. Any questions on that? All right, so then it turns out that the eigenvalues, these lambdas, so will capture the variance of the projected data captured by the corresponding eigenvectors. Can anyone tell me why that is? So we know that the variance of u transpose times xi, right, is equal to u transpose sigma times u. This was the algebra that we did on the previous slide. All right, so if here I have sigma x times u, I can get to its variance by just pre-multiplying it by u transpose, right? So now this entire term here is equal to the variance of the projected data along dimension u. And to make this equation hold, I have to multiply here by u transpose. Okay? But then this is just equal to lambda u transpose u. And that's just equal to lambda because we know that u transpose u is equal to 1. All right? And so the eigenvalue decomposition will give you corresponding u1 lambda 1, then a u2 lambda 2, etc. And these are usually ordered so that lambda 1 is bigger than lambda 2, is bigger than lambda 3, etc. And so it turns out that your u1 is exactly your dimension that captures the greatest amount of variance. Your u2 is your second dimension, orthogonal to the first, that captures the second most variance, and so on and so forth. All right. Any questions on this last slide? All right, so the derivation is over. And if we want to just implement PCA in MATLAB, this is actually how you do it. And so this is what you'll be doing on your actual homework. And so let's call y our neural data. So y was merely obtained by doing y equals r.spike raster, as you have all done on homework 4. and then binning it at some resolution. And so if y is your neural data, then we can do PCA in 3 steps. The first is we mentioned that we had to zero mean our data. So what we can do is we can just calculate the, so let's say that y here is a 96, the number of channels that we have, by time matrix. And let's say that we have, say, 15,000 bins. When I zero mean the data, what I want to do is I want to calculate the average firing rate, the average bin spike counts for neuron 1, and subtract it from every single value, right? And then I want to do the same for neuron 2. I want to find its mean and subtract it from every single value that I've seen. That'll mean center my data. And so what I really want to do is I just want to take a mean of my neural data for each channel. And so this will return a vector. Mean y of 2 will return a 96 by 1 vector, where the mean operation is just performed over all of the columns. And that's what this mean of y comma 2 is. And then this function bsxfun at minus is just saying to apply the minus operator to every single column of y and subtracting off this term. So what this will do is this will subtract off my mean of all of my neurons from every single column here. And so this is just a one-line way to mean center your data. You could also just iterate over all the neurons, average through time, and then subtract that. So anyways, all you want to do is you want to subtract off your mean for each neuron, each channel, from your time series data. And then after that, you want to calculate the covariance matrix. And so you would just simply calculate the equation that we had on the previous slide, which was sigma x equals 1 over n, and I'll just call this y here, y transpose. And so that's just this equation here. So this 1 over size y0 over 2 is my number of data points. And y0 times y0 transpose is exactly this term here. Then after that, all I do is I perform my eigenvalue decomposition in MATLAB. And so MATLAB has really great matrix operations. The function that we want is just called eig. And u times v will exactly be this eigenvalue decomposition that we saw in the previous slide, where the u's are eigenvectors, and the v's here are our lambdas. These are our eigenvectors, and the v's are our eigenvalues. And so MATLAB will be really kind and return you the eigenvectors and eigenvalues in the order that we want, where we said that lambda 1 is our biggest eigenvalue, lambda 2 is our second biggest eigenvalue, etc. And so from this, when we run this in MATLAB, we'll get that u colon 1, i.e. the first column of u, is the first PC. And v of 1 is the variance it captures. U, the second column of u, is the second PC. And v of 2 is the variance that it captures. All right? So that's how you perform PCA. Any questions on this? All right, so now that you have your matrix U and your eigenvalues V, what you can do is you can start to project your neural data. So let's say I wanted to project the neural data into my top 3 dimensions. So we'll call these x1 dimension 1, x2 is dimension 2, and x3 is dimension 3. And you'll see, because these u's were orthogonal, I can actually plot these axes orthogonally because my eigenvectors are orthogonal. And so if I want to project my neural data y0, the mean centered neural data, into these lower dimensions, all I have to do is take my first 3 PCs, right? And so this is a 96 by 3 matrix, where I have 3 columns, each one my first principal component, my second, my third. And then I multiply it by my neural data, which is 96 by time k. And so because of this transpose operator, I'll then get out 3-dimensional trajectories that are 3 by k. And if we call these x's, these are exactly our dimensionality reduced neural data into 3 dimensions. And they're the 3 dimensions that maximize the variability in the data. And so they're or equivalently minimize the residuals in your projection. Okay? Any questions on this? So really, the entire work of PCA, intuitively, was to just get out what the subspace is, what these projection vectors are. And that's just this U matrix that we got from our eigenvalue decomposition. And we can then just apply that U matrix to project our data into it. Okay, Anjali?
So when you have 96 by k, is
Yeah.
k just the number of time points, or are you stringing all of your trials together as well? So is k equal to the number of time points in each times?
Yeah.
Addition of all times?
So in the example that I gave on the previous slide, it would just be all of your trials strung together and then binned. But then in general, it could be whatever you want to project. And so let's say I just wanted to take all my trials to the right, like for a rightward reach. So you can imagine that each of these lines here represents one trial where the monkey reached to the right. Then this k could just be, you'll just concatenate all your neural data where the monkey reached to the right, bin it, and then the k is just the length of that vector. So k is just the length of the neural data that you want to project into your lower dimensional space. All right. And so this view of the neural data is actually capturing what the neural population activity is doing. So each trajectory, remember, we multiplied here u1 to 3 transpose y0. Each trajectory is actually combining the activity from all neurons into a lower dimensional subspace. And each neuron contributes to the overall trajectory. And what you'll see in your homework is if you actually look at the values of u1, so this is your first PC, you would see that they're non-zero for basically every neuron. And so each neuron is giving you a weight to your projected data. And those weights are captured in your principal components. And so because this view of the population of all 96 neurons, how they're evolving through time, because this view is capturing the activity of all of those neurons, we usually call this the neural state. All right, any questions on that? And then when we start to look at these when we start to look at these trajectories, we can start to make observations and new hypotheses. And so, for example, Nathan?
So, sorry, just to go back to that main idea.
Yeah.
Is there a reason particularly why we're choosing 3 dimensions? Is it just for, I mean, is there any further application, or is it just for visualization?
There are further applications. And we'll get to, yeah, so here we're only plotting 3 dimensions because that's all we can show you on paper. In a few slides, I'm actually going to show you how much variance, because you remember we got these eigenvalues that tell you how much variance you've captured. And so you would want to capture, say, 80 to 90% of the variability of the data. And it turns out that you need about 10 to 20 dimensions to do that. And so this is actually a great example, this slide here. The insight that we got from looking at the neural trajectories is that as the trajectory is going on, so red here is for this delay task, when the target comes up, the monkey's holding the center, the target comes up, and the monkey is beginning to plant to that target. The green here is when the monkey gets the go cue that he can actually reach to that target. And the blue here is when the monkey actually starts to move his arm. And you can see that as the trajectory is evolving, the spread in all these trials seems to be getting smaller. And so the spread in the blue points when he's actually moving is smaller than the spread in the green points, is smaller than the spread in the red points. And so this suggests that the variability across your trials is decreasing as you progress further along in the trial. And this was a hypothesis that several students in Professor Chenoy's lab investigated. And what they did is they calculated the variance of, or the volumes of these spheres, capturing the variance of this data. But they didn't do it in 3 dimensions. They did it in many more dimensions, because you always have to check that your hypotheses are valid in the appropriate dimensionality of the data. All right, so we just have 5 minutes. I just want to finish a few slides. And so the first slide will address Nathan's question, which is how many dimensions do we actually use? And so what I'm here plotting is on the x-axis, the number of dimensions, So for here, we had 220 neurons for this monkey. And what we plotted here is for dimension 1, we saw how much proportion or what percentage of the variance was captured. And so this would just be lambda 1 over sum of I equals 1 to 220, the number of neurons of lambda I. So this term in the denominator is the total variance, and lambda 1 is the proportion that that just dimension 1 captures. And then we can see how much variance is captured by the first 2 dimensions by then adding plus lambda 2. This is the variance captured by the top 2 dimensions, the percentage of variance. Plus lambda 3 would give us the variance, the proportion of variance captured by the top 3 dimensions. And what we can do is we can then just say, how many dimensions do we need to capture some amount of variance? And so if I use all 220 dimensions, I would capture 100% of my variance. But it turns out that if I just actually want to capture 90% of my variance, that I only need something like 20, maybe 25 dimensions of the data. And so this is really cool because now in your top 20 or 25 dimensions, you're capturing most of the variability of the data. Now there's some variability that is actually noise, right? Because we are calculating these across the neural data, and we know that the neural data is noisy on single trials. It has Poisson statistics. And so it actually turns out that, that maybe this 10% of variance here is actually corresponding to noisiness that actually isn't really correlated at all. Remember, the PCs are capturing correlated noise. And so this could actually be a way to denoise your neural data for neural prostheses, because you would imagine that your important signal variance related to my movement is actually just captured in these correlated dimensions, in these first, say, 20 dimensions. And then if I throw away dimensions 21 to 220, those dimensions could just be capturing noise. I could have actually just denoised my data. And maybe I get better neural prosthesis performance out of this. And so that's an application of PCA, where we say that we find empirically that actually the top 10 to 20 dimensions capture all the meaningful signal variance in the data. And these other dimensions, 21 to 220, which do capture variability in the data, could very well just be noise from spiking rate statistics. So there's this optimization that we have to perform where we want to choose the dimensionality carefully so as to not inadvertently throw away signals. So we want to make the dimension high enough so that we capture all the signal variance. But we also want to keep it low because when we get to, say, dimension 50, we're probably just including noise, right? Each of these dimensions above dimension 50 is capturing less than 1% of the variance. So this plot is not rising very much for each dimension that we add. And so there are several ways that you might think of doing this. One way is you could build a neural prosthesis, and you could calculate your mean squared error in decoding, as you've done in homework number 4, for varying the number of principal components. And that could give you a measure of what the optimal number of PCs is. I was going to talk about another way that you could cross-validate the number of PC dimensions, but we just have 1 minute, so don't worry about these slides. This was another way that a student in Professor Chenoy's lab was able to cross-validate the dimensions and show that it was about 10 to 20 that was optimal. But I just want to end on our last slide here, which is coming back to the big picture, which is we want to look at dimensionality-reduced data. And so what are some of the cons of PCA? So we found that PCA could find us these linear directions, these axes that capture a lot of variability in the data. But we know that a neuron with a higher firing rate has higher variance, right? We know this from handouts 7 and 8, where the Fano factor of a neuron is equal to 1. So if it fires faster, it has higher variability. And because PCA is trying to find dimensions of highest variance, higher firing rate neurons may dominate those dimensions. And so we can get around this somewhat by just normalizing the firing rates so that they instead go from 0 to 1. And so we can just divide the firing rates that we see by the range of the firing rates. A second thing that there isn't in PCA is a noise model. And so like we saw that there was in the Kalman filter, these noise models can be really useful and can really improve the dimensionality reduction, because instead of finding the directions in which the data has just the greatest variance, you can start to look at the dimensions at which the data covaries together. Their noise is correlated. And so this is a technique, techniques like factor analysis or probabilistic PCA, which are covered in classes like CS229, can handle. We'll introduce to you other dimensionality reduction techniques that incorporate such noise models. And then almost surely, the data don't exist on a linear manifold, on a linear subspace. And so what we would really want is nonlinear dimensionality reduction techniques that allow us to find curved manifolds over which the data lives. And this is a topic for classes like EE378B, in case you're interested. All right. Any questions? Maybe we can take one question and then we'll break for the day. Yeah.
Yeah, do most people use linear, or have we moved over to non-linear techniques? In practice,
Yeah.
how often are we using this?
In practice, we are mostly using linear techniques still.
Okay.
Yeah.
And that's because it gets most of the 20 dimensions.
It gets most of the variance, but then also it turns out that these nonlinear dimensionality techniques aren't easily used for cross-validation. So if I got my PCs, my U's from 1 to 3, then I can project anything into those dimensions by just multiplying it by any neural data. And it turns out that you don't get this simple operation for nonlinear dimensionality reduction. You can actually only just calculate what those embedded manifolds look like from the data that you have, but you can't do it for data that you haven't seen yet. All right, have a good rest of the day, everyone.